In this lecture, we are going to discuss about an important theorem of sequence of real number. And in this theorem, we state the condition under which a sequence of positive real number is convergent. Okay? And the statement is, if un be the sequence of positive real numbers such that limit n tends to infinity un plus 1 by un, this is equal to L. That is the ratio of n plus 1th term and nth term, this is equal to L. And this theorem says that if 0 less equal to L less than 1, then the limit of the sequence as n tends to infinity, this is 0. Okay, that is this sequence converges to 0, and we say that in this case this is the null sequence, right? This is the null sequence. We know that the definition of null sequence is sequence which is converged to 0, then the sequence is said to be null sequence. And if this limit L is greater than 1, then this must be diverged to infinity. Okay, and if we get the limiting value of this ratio is equal to 1, then we cannot make any definite conclusion about un. Okay, these three are three different cases, and here L is not negative because it is said that this is a positive real sequence. Okay, or sequence of positive real number. After proving this theorem, we take some important example or we take some important application of this theorem one by one. Okay. To prove this case, we first let that since here limit n tends to infinity un plus 1 by un, this is equal to L. So from the definition of limit of a sequence, we choose that for any pre-assigned epsilon greater than 0. Okay, pre-assigned means we can choose epsilon, the value of epsilon, as we want. Okay, so for any pre-assigned epsilon greater than 0, there exists a natural number k. This is natural number k such that mod of un plus 1 by un minus L less than epsilon for all n greater or equal to k. This is the definition of limit of a sequence. Okay. Now expanding the modulus, we get the result as un plus 1 by un minus L. This is less than epsilon and this is less than minus epsilon. Okay, and this is n greater or equal to k. Now we add L on 3 parts and we get the result as L minus epsilon less than un plus 1 by un less than L plus epsilon. This is also for all n greater or equal to k. Okay. Now we take the case that is the first case. In the first case, it is said that in the case 1, it is said that 0 less equal to L less than 1. Okay, that is here L less than 1. And since we already says here epsilon is pre-assigned, so and here we write and we choose epsilon greater than 0 such that L plus epsilon is less than 1. For example, if L this is equal to 0.9 which is less than 1, then for this case we can choose epsilon this is equal to 0.01, and it is clear that L plus epsilon this is equal to 0.91. This is also less than 1. So we choose epsilon as like this. Okay, so we get the result as L plus epsilon less than 1. Now from here we can write the result un plus 1 by un less than L plus epsilon, and this is for all n greater equal to k. We take only these two parts, that is middle portion and right portion, and here we let L plus epsilon, this is equal to r. Okay, we name this term L plus epsilon, this is equal to r. So we can write this is equal to r. So we get this. Okay. Now since this result is hold for all n greater equal to k, so we put n, this is equal to k plus 1, k plus 2 to n minus 1 in this relation, and we put this value of n 1 by 1 here. We get, by putting n equal to k, we get uk plus 1 by uk less than r. By putting k plus 1 in place of n, we get uk plus 2 by uk plus 1 less than r, and so on. If we put the last one n minus 1, we get n minus 1 plus 1, this is n minus 1 plus 1 by n minus 1, this is less than r. Okay, now we multiply all of them vertically, we get the result. If we multiply this, okay, then we write here uk plus 1 by uk into uk plus 2 by uk plus 1 into, and so on. The last term is un by un minus 1, and the right side is less than. Here the number of r is given by, we put n equal to k to n minus 1. So the number of r is given by r to the power, this is n minus 1 minus k plus 1, this minus this plus 1. Okay, so this is n minus k, and it is clear that uk plus 1 cancel out, uk plus 2, here uk plus 2 is present, so cancel out, and we get only two terms. This is the uk and this is un, and this term is also cancel out with this term. So we get the result as un by uk less than r to the power n minus k, and here we must write n greater equal to k plus 1. Okay, why we write n greater equal to k plus 1? Because if we take n greater equal to k, then n minus k, if n greater equal to k, then we may take n, this is equal to k, because here equal to sign is hold. So this side is r to the power 0 maybe. So this side is r to the power 0 means 1. For this reason we take n greater equal to k plus 1. Okay, so we get un less than r to the power n by r to the power k into uk, and un we write this is less than uk by r to the power k. This is the constant term because this is independent of n, and here r to the power n is present. Okay, and we let L plus epsilon, this is equal to r. So from here we get r less than 1. Okay, and since r less than 1, so we know that r to the power n, this is tends to 0 as n tends to infinity, because if r is positive and less than 1, then if we increase the power of r, then the total value is decreased to 0. So we can write that un less than this term, and this is tends to 0 as n tends to infinity. Okay, but in the right side there be un, so we get the result that limit n tends to infinity un, this is equal to 0. Okay, so we prove the first case if 0 less equal to n less than 1. This is the case and this we proved here. And for the second case, if L greater than 1, then we take these two portions, left portion and middle portion. Okay, and here it is given that L greater than 1. So L greater than 1 here, L greater than 1. Here the second case, this is L greater than 1. Here L greater than 1, and we choose epsilon greater than 0 such that L minus epsilon, this is also greater than 1. Similar manner, if we take L, this is equal to 1.001, then we take epsilon, this is equal to 0.0001. Then if we make the operation L minus epsilon, then this is also greater than 1. Okay, so if L is approximately equal to 1, then also we can choose epsilon greater than 0 such that L minus 1, this is also greater than 1. Okay, and here if we take this is S, then we can write this is S greater than 1. Okay, and from this relation we get un plus 1 by un, this is not less than r, this is for the second case, s less than un plus 1. Okay, and also here we put n equal to k, and the same way we get this result, but here this is not right side result, we get the left side result as less than s and also less than s. And here if we multiply all the result vertically, then we get here in the left side, this is s to the power n minus k, right? And we get the result here, this is less than s to the power n minus k. Clear? So we write from this relation, we write separately from this relation un greater than s to the power n minus k into uk, and similarly we write un greater than uk by s to the power k into s to the power n. Okay, here also this term is a fixed term because here this is independent of n, but only dependent on n term is s to the power n, and here s is greater than 1, so s to the power n must be infinity as n tends to infinity. Okay, so we write that this is tends to infinity as n tends to infinity. So from this relation we can write that limit n tends to infinity un, this is equal to infinity for the second case. Okay, now we go to the third case. When L equal to 1, then we cannot make any conclusion or any definite conclusion. For this result, here we have to choose any two sequence whose limiting value is 1, but we cannot make any definite decision here. Okay, we consider here two sequence un, this is equal to n plus 1 by n, and un, this is equal to 1 by n. And for the first case, if we find un plus 1, and this is given by n plus 1 plus 1 by n plus 1, so n plus 2 by n plus 1. Okay, now we find the value of un plus 1 by un, which is given by n plus 2 by n plus 1 into n by, this is n plus 1. Okay, and getting the result as this is given by if we divide numerator and denominator by n square, we get the result as 1 plus 2 by n by 1 plus 1 by n whole square, and clearly this is tends to 1 plus 0 by 1 plus 0 whole square, and this is must equal to 1. So here we get L this is equal to 1. Okay, L this is equal to 1 we get for this case L equal to 1, but we know that un this is 1 plus 1 by n, and the limit of this sequence obviously this is 1. Okay, so this is not 0, sorry. So in this case the limit is 1. But if we consider the second case, then here un plus 1 by un, this is given by 1 by n plus 1 into n by 1, and getting the result as 1 by 1 plus 1 by n, and this is tends to 1. This is L. Okay, here also we get L equal to 1. But in this case un this is equal to 1 by n, this is tends to 0. Okay, so in both case L equal to 1, here also 1 and this is also 1, but the limiting value of un, that is the un converts to 1 and here un converts to 0. So the limit of the sequence are different, but the limit of the ratio un plus 1 by un, this is in two places is 1. So we say that if L equal to 1, then we cannot make any definite decision. Okay, so this is three cases of the value of L. Now using this theorem, we get an important application. This application is taken from exercise of your textbook. Okay, here it is given that prove that the sequence un is a null sequence. We already says that what is null sequence. If the limiting value of un this is equal to 0, then this sequence or this type of sequence is said to be null sequence. Okay, so for the first case, if we take un is this, so we find first un plus 1. This is n plus 1 factorial by n plus 1 to the power n plus 1. Okay, now un plus 1 by un we find, so n plus 1 factorial by n plus 1 to the power n plus 1 into this is n to the power n by n factorial, right? So we get n plus 1, this cancel out, here remaining term is n plus 1, and this is given by n plus 1 into n plus 1 by n to the power n. We divide n to the power n in the lower term. So n plus 1 cancel out, and we get the value as 1 by 1 plus 1 by n to the power n. And we know that the value of this sequence 1 plus 1 by n to the power n, this is very popular sequence, and this is, we know that the value of this or limit is e. Okay, so we get this is tends to 1 by e, and since the value of e is lies between 2 and 3, so 1 by e must be less than 1. So we get the first case here 0 less than less 1, and by using this theorem of sequence we say that limit n tends to infinity un this is equal to 0 for the first case. Okay, and similarly by using this theorem we can also prove second and third problem very easily, and these two are your home task. Okay, these two are home task. Very easily we can show this and this are also null sequence using this theorem. Very important theorem, and we also solve here a problem from your exercise. Okay, thank you for watching.